So we start with cellular solidification. So here we have these three regions: solid, messy, and liquid. In messy, basically have both the regions solid in this region and then liquid in this region. So as we can see, the concentration profile is somewhat like this. In this region, we can approximate this profile to be linear, and then we have this non-linear region. So here the something which makes cellular solidification different from plane front solidification is here we have a solute redistribution in both the direction. In this direction, which is the direction of solidification, as well as the direction which is perpendicular to this. So we have this liquid gradient in this direction, as well as we have liquid gradient in this direction. So in order to solve this problem, we make certain assumptions. These assumptions are: first, we assume since there is not significant gradient in this direction, we make the first assumption that there is no thermal gradient in this y direction. That means that the planar fronts are isothermals. The second thing is that constitutional supercooling is helps in minimizing the cell spacing. So to simplify this problem, we make certain assumptions. These assumptions are: there is no gradient in y direction, which would mean that these planar fronts, these are isothermals. The second assumption is constitutional supercooling minimized by cell spacing. So we assume that the supercooling in these regions are absent or kind of absent as they are minimized by the cell spacing. The third assumption is there is not significant curvature effect, and the fourth is no solid state diffusion. That once the solid form remains at the same concentration. So to obtain the final equation that we obtain for this solute concentration is CS star, which is the concentration of the solute. Let's say this part. So we'll get the concentration of this interface. At this interface, what is the concentration? This will be the CS star. Then we have this K, which is the partition ratio. We have C naught, the overall concentration. Then we have one parameter A. Again there is a K, and K minus 1 plus 1 minus A by K minus 1 into 1 minus Fs raised to the power K minus 1. Fs is the fraction of solidified. So what is it? So A is a parameter which is equals to dlg by ml rc. So from where we get the relation? So in order to get this, we first obtain this relation from the phase diagram. So this is how the phase diagram looks like. So this region, let's say we start with a concentration C naught. This is the concentration C naught. This temperature is TL, and as we go down, we encounter solids with different concentrations. So let's say this is some concentration CS1 or something. So this is Cl, which is this concentration. So we get this relation. This is the slope of the line ml, and this temperature is TL, and the temperature just below is T. So we get this relation: Cl minus C naught is equal to 1 by ml T minus T. This is trivial one. And when we differentiate this equation with respect to this distance x, we obtain this relation: del Cl by del x is equal to G by ml, where G is the thermal gradient which is applied externally, which is basically del T by del x, which we apply externally. So we obtain this relation that del Cl by del x is equal to G by ml. Also from the steady state equation, there should not be any solute accumulation, which implies that R, where R is the velocity of this interface, the velocity at which this interface moves. RCT minus C naught equals minus del Cl by del x. This is the relation that we obtain from Fick's law. So using this relation, as well as using the value of del Cl by del x from this relation, we obtain this Ct to be equal to 1 minus A times C naught. And from this we get the this relation is something where we use this parameter A, and the value of this parameter turns out to be dlg by ml rc naught. Here we define an effective partition ratio, which is basically KT is CS star by C naught, where CS star is the concentration of solid over here. So this is the CS star. So this is called effective partition ratio.
Our next topic is laminar eutectic growth. The mechanism of eutectic growth in a non-facet alloy has been treated by Jackson and Hunt in a simplified way through laminar eutectic growth. Let us consider an alloy of exactly eutectic composition growing with the plane in front. Expect that the individual lamellae have slightly curved surface. As we can see in the figure, it shows the undercooling and interface composition Cl star of an eutectic alloy at a point on the interface in front of alpha phase. The figure A shows the phase diagram of that, and the B shows the interface showing the point y1 for which the construction of A applies. As the alpha phase grows, it rejects B atom into the liquid, and as the beta phase grows, it rejects A atom into the liquid. So there is a buildup of B atom in front of alpha lamellae, and there is a buildup of A atom in front of beta lamellae. For equilibrium, there must be an undercooling in front of the lamellae, which depend upon the amount of solute buildup or depleted, and the slope of the liquid is curved TL infinity. The equation is delta TD equal to delta TE minus TL infinity equal to ML CE minus CL star. Delta T is the undercooling due to solute diffusion, TE is the equilibrium temperature, and TS and ML equal to depleted slope. CE is the composition at eutectic, and CL star is the composition at a distance y. The quantitative treatment of the eutectic growth begins with a description of solute diffusion filled in front of growing lamellae using the differential equation del square Cl plus R by dl is del Cl by del x dash equal to 0, where Cl is the liquid composition at x dash and y dash, and the x dash is the distance in growth direction measured from the liquid solid interface. Y is distance transverse to growth direction and to lamellae. R is the growth rate, and dl is the liquid diffusion coefficient. And for this we have taken the approximation that liquid solid surface is small, and delta T is so small that Cl equal to Ce, and the composition of the solid phase formed are of equilibrium concentration at eutectic temperature. And the boundary condition are as Cl equal to Ce at x dash equal to infinity, and del Cl by del y equal to 0, and y equal to 0, and y equal to S alpha plus S beta. In this figure, we see that the actual interface temperature T star must be essentially constant in non-facet eutectics. This is because the curved surface of the lamellae in these eutectics usually deviate from a plane by less than a few macron. Hence, even if the temperature gradient exists in the growth direction, the variation in the temperature from the leading to the lagging part of the lamellae is negligible. The interface is maintained isothermal at T star by the lamellae adjusting their radius of curvature locally. This figure shows a systematically result of calculation for a typical example of eutectic growth. Maximum composition deviation from the eutectic is small, that is usually less than 0.1%. Moreover, even this small deviation is happily damped out at small distance in front of the interface. For example, at a distance x dash equivalent to S alpha plus S beta, the liquid composition difference essentially disappears. The distance S alpha plus S beta is half the lamellar spacing, which is sum of the width of an alpha and beta lamellae. The fineness of the lamellar structure is usually described in terms of this interlamellar spacing. Typically, they are 10 micrometer and they are decreasing with increasing growth rate. For determining quantitative curves, we need to specify only lamellar spacing and growth rate. And however, to specify delta TR, T star must be constant, and this is done by specifying the angle between the tangent to the lamellar surface at the lamellar edge and the growth direction. Assuming equilibrium at the lamellar boundary juncture with the liquid, these angles are as required by the force equilibrium, which we can say that sigma alpha L cos theta alpha plus sigma beta cos theta beta equal to sigma alpha beta. Using theta as a junction along with the lamellar thickness information, full shape of the lamella can be obtained. This figure shows lamellar spacing as a function of growth rate in tin lead composite. This is a result of Cadwick and Davis. And for a fixed interface velocity, this model can be satisfied by a range of delta T and lambda, where lambda is the lamellar spacing. However, experimentally for each R, only one spacing is obtained. Possibility is that the system adopts the spacing for a minimum undercooling for a given velocity or maximum velocity for a given undercooling. Hunt and Jackson have shown that after establishing a laminar spacing at one growth rate, spacing can be maintained even though velocity is subsequently significantly increased. Growth rate could not have been at the extreme both before and after the velocity increase.
Going to discuss dendritic arm spacing. Dendritic morphology in case of casting and ingot making process remain largely unchanged over wide range of cooling rate. I mean to say that in case of casting, it doesn't depend on cooling rate. Okay. As we are going to extract heat, in this case, as we are going to extract heat on the greater and greater rate, it will become more finer and finer. At the very high cooling rate, primary arm spacing become very small, and hence secondary and tertiary arm disappear. Dendritic arm spacing is a measure of solidification of dendrites. If spacing is too close, then one or another arm fall behind or melted away. If the distance between two arms is very large, then in that case what happened, it will grow secondary arm or tertiary arm. The driving force for this is constitutional solidification, as in the case of as suppose dendrite are growing like this, then along this direction composition is not constant. Solid composition is not constant. It varies, and therefore temperature gradient varies. And this is what we call constitutional solidification. Solidification depending upon the composition, not due to temperature. This is constitutional. Therefore, the driving force for this process is constitutional solidification, and this is overcome by formation. This is overcome by dendrite. In dendritic case is by formation of a new branch. Now we discuss dendritic primary arm coarsening. Primary arm coarsening is explained by three models: Model 1, Model 2, Model 3. Model 1 says in first model, radius of dendrite is considered to be constant. Suppose it is A, and except for one arm whose radius is R0, which is less than A. The melting point of a smaller arm, I mean this arm, is less than the melting point of other. Therefore, this arm will melted because of transport of material from smaller arm to larger arm. Hence, the local dendritic arm spacing increases. As this arm disappears, therefore distance between the arm increases, and hence this is going to lead to coarsening of the arm. In case of second model says that a dendritic arm is considered whose root is slightly smaller than. In this case, root of this arm is slightly smaller than its remainder part, and this arm tends to melt away by transport of solid from necked region. This solid particle are transported from this necked region, and hence it has disappeared, and finally we got a small which get melted away in that. In case of third model, a dendritic arm of radius A is considered. The two-fold radius of curvature at its tip causes it to melt off by transport of material to a cylindrical shape, which leads to. In all these three cases, first model is easiest to describe quantitatively. Coarsening also occurs during isothermal heating. This implies if the total solidification time is longer, then the coarsening will larger. It can be explained by the graph